Yes, thank you. Looks like the sound is working here. Can you hear me over there? If all is good, and continue. Yes, good. Thank you. So I had in mind the ordering of the topics, which I then reversed to the last moment. But I think this one works better because I need to talk a little bit about the Toda space, and there's some algebraic geometry properties involved, and the natural place to display that is in connection with Coulomb branches. And then in my second lecture, I'll discuss the application to Gromov-Witten theory of Fano manifolds. So, okay, let's see if my trick is working. Oops, not yet. All right. Yes, it is working. All right. So, a recent understanding in mathematics and much older understanding in physics is telling us that some features of three-dimensional gauge theory, especially its topological limit, are controlled by certain hyperkähler spaces closely related to the Toda integrable system. That's specific to three-dimensional supersymmetric gauge theory. And the broader pattern behind that is that if you study the low energy behavior of a quantum field theory, you expect that to be related to what people call a sigma model, taking value in the moduli space of vacua of the theory. So this moduli space, if you can really work out what it is, should be controlling the very low energy behavior of your theory. In particular, there's a topological sector that should be controlled, determined from the moduli space of vacuum. And I'll just display this in one block because a long history of results on the subject. So probably the earliest I could find is Zyberg and Witten, the early 90s, who studied the modular of vacua for pure 3D gauge theory for the group SU2, and they found the Atiyah-Hitchin manifold as an answer. That was then pursued and generalized somewhat by Argyris and Faraghi, who for SUN posited monopole moduli space. That was actually a correct and somewhat justified guess for the answer. Warner also proposed generalization to other Lie groups. And about also in the 90s, Zyberg and Intriligator introduced 3D mirror symmetry. It's something I'd very much like to learn about, but I don't think I understand, and probably the audience knows more about it than I do. And then somewhat later, Witten and Haneni wrote down the Poincaré series for the chiral ring, for a ring of functions on the space of vacua for gauge theory with a linear representation, linear matter fields. Independently of that, and actually it may have been slightly earlier, there was a landmark result which at the time was not, I think, placed in connection with the questions of gauge theory and the modular of vacua, namely Bezrukavnikov, Finkelberg, and Merkovich gave a topological description of a Toda space in terms of a homology of affine Grassmannians. We're going to see that later. So at the time, that was a completely parallel research and hadn't yet converged with that. Then some years later, yours truly pointed out that Gromov-Witten boundary conditions for 3D gauge theory. So first of all, Gromov-Witten manifold, symplectic manifolds with Hamiltonian G action should give rise to, by means of a Gromov-Witten theory, to boundary conditions for 3D gauge theory, and they should correspond to holomorphic Lagrangians in the Toda space. And now returning to the main line of finding out what the moduli of vacua are, there were a series of papers in rapid succession. First, Nakajima wrote some proposals, then Bullimore, Dismofti, and Gayotto wrote a long paper describing what the structure of these things should be, but in particular, they completely determined the Coulomb branches for torus group and their representations. And very shortly after that, Braverman, Finkelberg, in collaboration with Nakajima, wrote down a proposal for what I call the chiral rings in the case of gauge theory with matter in a quaternionic representation, which is a double of a complex representation. So there's some distinction to be made here. When physicists talk about Coulomb branches, they mean the entire geometric structure on the moduli, on one component of the moduli of vacua, namely the hyperkähler metric. If you pick a particular complex structure, you're going to get a complex manifold with a holomorphic symplectic form, or Poisson structure at least, and that is the ring of functions on that they call the chiral ring. So there's a slight discrepancy in the literature, it seems, between what physicists call Coulomb branch and what's being used now in mathematics. So I think what we're discussing now in math are the chiral rings. In the case of the zero representation, the total space, we actually know the hyperkähler structure. And I believe, but I couldn't locate the reference, in the abelian case, people can write down the hyperkähler structure as well for a general representation. Well, so continuing, the most recent thing was a proposal by a group of authors, including Braverman, for what the chiral ring should be when you have a representation of the group which does not split as a complex representation plus is dual. It's a quaternionic non-split representation. First example would be the standard representation of SU2. It's not the sum of two one-dimensional representation. And finally, I think I wrote a paper sometime last fall where I give a construction of a chiral ring strongly inspired by the original Braverman-Nakajima construction. So I think that's where we are, although there's a lot of research involving a connection of geometric representation theory for the specific Coulomb branches, but I don't know so much about that line of argument. I'm concerned with the three-dimensional gauge theory, its boundary conditions, and what it says about in topology.
Constantin, hey.
Yes.
This is Tudor. Just to make a comment on hyperkähler structures, which seem to still be relatively unexplored here. So in our paper, we sort of explained the map between a Coulomb branch for a group and a Coulomb branch for the torus locally, and gave a proposal for how to upgrade. So in an abelian case, you can completely write down the entire chiral ring as sections over twistor space. And that determines the hyperkähler structure. And there's a proposal for how to upgrade that to any non-abelian theory with polarized matter that it would be nice to do more with. Sorry, just throwing that out there.
No, I completely believe that, and I have nothing to say about the hyperkähler structure except in the cases where the original case is more or less where it's known for a different reason, which is realization of the space of solution to NAMS equations. Actually, that's the only case I know. So anyway, everything I'll discuss has to do with what we call the chiral rings. So I will not attempt to even propose anything, but thank you for the reference. All right, let's keep going with this. I'm now committed to this system. So in supersymmetric gauge theories, I mean, that's a comment maybe that I should have made even before writing the list of references. There are two distinguished components, supposedly the moduli of vacua, the Coulomb and Higgs branches, and the Higgs branch in the case where, well, at least, sorry, for gauge theory of a group acting on a hyperkähler manifold, the Higgs branch is meant to be simply a hyperkähler quotient, whereas the Coulomb branch, at least when X is a linear space, is going to be the toda system plus what people call sometimes quantum corrections, which means in all examples known, it's birationally equivalent to toda systems. But so I think that shows you have an easier task understanding the algebraic geometry of the chiral ring than you will the metric. So in fact, the examples I'll explain, I think the algebraic geometry is under control, whereas hyperkähler metric is you'd have to ask Tudor, I think, to tell you how one could get one's hands on that. All right, so now, unfortunately, because of a time difference, I wasn't able to take part and see the other lectures. I'll probably say something that have been already mentioned. In that case, just note that, or tell me that I should just speed up when going through this. So the first ingredient I want to remind you of is, or are, if you like, the toda spaces, which are the Coulomb branches for pure gauge theory, for the zero representation. And what we know about them, I think, built over time, I mean, they go back, of course, decades, the original construction. We know they're hyperkähler manifolds. In one of the complex structures, they are completely integrable, 1 billion groups over their bases. And the bases are, so maybe I should add, why do I write 3 and 4? Bad notation. What this is meant to convey is this, in mathematics, this goes with homology. This goes with K-theory. And one way to, approximate way to explain that is they come from, by reduction from 4 dimensions, and you could either reduce along a line, translation invariantly, and then you get this, or you can reduce along a circle, translation invariantly, but then the topology will still see something. You'll see an equivariant parameter for circular rotation. And if you invert that parameter, that becomes the Bott periodicity operator in K-theory. And I think in a consistently with many other examples, you then get, instead of, if you have a homological description of the original story, you should get a K-theoretic description of a new story for the circle action. And that happens in many cases. So the basis for these spaces are the equivariant homologies or equivariant K-theories of a point. And Toda spaces themselves are 1 billion groups over these bases, which are also holomorphic or algebraic, even integrable systems. So they have a group log along the fiber and the unit section. In the abelian case, of course, very easy. They're just the cotangent bundles of the Langlands dual tori or the periodicized cotangent bundle of the, this is the Langlands dual torus in both cases. The homological version uses the cotangent bundle of that. The K-theoretic version uses the periodicized cotangent bundle of that. And note that the cotangent fiber here is, of course, the original dual, the original Lie algebra of the torus. In general case, the space can be described as affine blow-up of the Weil quotients of these fellows by the Weil group in the non-abelian case. And affine blow-up means you, they blow ups and you remove some divisors to make them affine, but Bezrukavnikov, Finkelberg, and Merkovich gave explicit description of what functions you have to add to the rings of functions to produce the blow-up. So they're explicitly known. But the more interesting description, conceptual description they gave, connected with homology, and namely they found that C3 was the equivariant homology of the based loop group of G. C4 was the equivariant K homology. And this carries 2 multiplicative structures, a Pontryagin product. So first of all, a natural product in equivariant cohomology and K-theory. So that's from the base. But as far as omega G goes, you have a Pontryagin product or a coproduct because we're dealing with homologies. So together, they give a Hopf algebra structure over the base, and that is the abelian group structure mentioned earlier. They also describe the Poisson structure, which defines the symplectic form, and so on. But I'll skip that for now. And sometime after that, using their description, I pointed out that first, some boundary conditions for 3D topological gauge theory should correspond to bundles of categories with Lagrangian support on these spaces, holomorphic Lagrangian support on these spaces. That was inspired by a proposal of Kapustin, Rozansky, and Saulina about what 2-category should give rise to Rozansky-Witten theory. So I now know a construction of something like a 2-category going for these particular spaces, but not for a general holomorphic symplectic manifolds. And I was specifically motivated by examples, namely symplectic manifolds with Hamiltonian G action should give boundary conditions for 3D gauge theory because they are 2-dimensional gauge theory by Gromov-Witten theory, which carry a G symmetry. And there are actually 2 somewhat different styles of examples. One of them involves open manifolds, in which case you have to look at the symplectic cohomologies. and the other one involves compact manifolds, in which case you need the quantum cohomologies. And the distinction between these will actually play a role in a description of the Coulomb branches between the open and the compact case. And here are the examples I'd like to go through fairly quickly. They are very old, some of them. First is a point. That gives rise to Berlinde formulas and their cohomological versions, Witten's integration formulas. The second one is a complex representation. And this gives generalized Berlinde formulas and also leads us to the discussion of Coulomb branches. And the third one is compact Fano manifolds that I'll leave for tomorrow. So these will be the examples of exploiting this holomorphic geometry of a Toda system in connection with gauge theory. So that will happen. All right, so let's look at the case of a point, first of all. This is very old story. So to get anything very interesting, you need a bulk deformation of the gauge theory. Bulk deformation, because you have a point, only comes from the cohomology of BG, and the cohomology of BG always has interesting classes in H4. If G is simple, it's essentially only one class, otherwise in invariant quadratic forms. So I'm going to take invariant quadratic form, function in the Lie algebra, and the way to introduce this deformation in the setting here is as a superpotential. So I'd like to point out what we're describing now is a mirror of gauge theory. So what you have to do here is the B model side of what you would have wanted to do on the topological side. So what do we do with the superpotential? We take the graph of a differential. Normally, you would draw it nicely in the cotangent bundle of your base manifold, but instead of a cotangent bundle, we have these integrable systems here with periodicized fibers over the base. So the base is now, this is the base in both cases. So here, instead of, actually, it's not obvious how a quadratic function defines a function conjugacy class of a group, but it does. It's just very multi-valued. So it is a valid superpotential. So you take the graph of differential, which you have to exponentiate to draw it inside these spaces. That gives a Lagrangian inside. And this meets the unit section of the Toda group scheme at certain lattice points in the Lie algebra, or Weyl orbits in the non-abelian Lie algebra, or in the torus, mod Weyl. And the Hessian determinants at these points, at the intersection points of W, are the structure constant for a Frobenius algebra. So you get a semi-simple Frobenius algebra based on the functions at those intersection points, which are transverse. And the structure constant comes from the Hessian determinant, and that determines the two-dimensional TQFT, and that actually is the two-dimensional TQFT of point mod G, pure gauge theory in 2 dimensions with bulk deformation coming from the cohomology class in H4. In other words, you get the integration formulas of the moduli of bundles, or index formulas for line bundles, which are the famous Berlinde formulas, just from this picture. So that's a description of those. Actually, something amusing to draw here. I didn't leave myself space. Maybe I'll draw it. Or maybe I won't draw it. I mean, there's a very nice way to explain something that you may know. So you may know there's a difference in the Berlinde formula one difference between the abelian and non-abelian case is that, well, the points in question, the maximal torus, the Berlinde points are roots of unity, or torsion points. But in the non-abelian case, the unit itself and in general singular conjugacy class are not valid Berlinde points. You're leaving them out in the Berlinde formula. And you should, because the formula actually blows up at those points. And there's a very nice explanation in this Toda picture, because what happens is that that's precisely where the non-abelian Toda space gets blown up compared to the torus version. Because of that blow up, the graph of this differential does not intersect the zero section at that point. So what happens is exactly what should have been happening if you looked at the formula in this respect. All right, let's make it slightly more interesting, building up to chiral rings. Oops, that will not work. Have to find a faster way to do this. So let's take a linear space, so represent a complex representation of V modular G. And actually, this is meant to be the A side of the theory. So even though V is complex, you want to think it's a symplectic vector space, symplectic space with Hamiltonian G action. That's what it really is. But non-compactness tells you that to get something reasonable, you need to compactify it, quote unquote, by introducing the C star scaling, at least that. You could introduce several scales if you can. That will render some formulas like integrals over V finite, a covariant integration. And when you introduce the C star scaling topologically, that comes in as an equivariant parameter mu. That's of course in H2 of BC star, Bu1. And that's called the complex mass parameter in physics, if I'm not terribly mistaken. All right, so now the Lagrangian in the mirror side, which is the B model side in the total system, the Lagrangian I need to look at is again, this doesn't make sense, it's a little backwards, is the graph of the exponential of the W. It's a total system. Where W again is a superpotential now for the gauge linear sigma model. And there's an H star in it's a homological in the K-theoretic version. The homological one involves some logs, the K-theoretic one involves some dilogarithms. I'll just write explicitly the exponentiated differential, which is the map that sends a point in the Toda base, to this Euler class-like product, a product of powers of linear functions in the base variable of a Toda system, the mass parameter and the Lie algebra variable. And similarly for the K-theoretic version, you need a function from the base torus to the dual torus, which is Weyl invariant, and that has a formula that reminiscent of the first one, using something looking like a K-theory Euler class, then raised to a power to map in the dual torus. And you see how the mass parameter helps to regularize this thing, right? When this linear function vanishes, you don't land in the torus to get singularities, but you can think that if mu is very, very large, then you could say, well, this is not really zero, and then it really does land in the torus. So near infinite mass, formally, this is actually a unit and is well defined, and the singularities only appear when the mass becomes finite. And the theorem, which is an old result of myself with Chris Woodward, generalizing some formulas of Witten's, is that if you compute the TQFT from this superpotential in the exact same way by intersecting with the unit section and using the Hessian determinants at those intersection points, what you control is exactly the gauge Gromov-Witten theory V mod G, or at least I should be honest, we didn't look at moving curves, just look at a fixed curve. So I should say the quantum cohomology, a covariant quantum cohomology of V regularized by mu. So that was a little bit of an optimistic misstatement in Gromov-Witten theory. So this, in fact, it's open how to, open question, extend to kappa classes, extend to moduli of curves or moduli of curves. Actually, one of my graduate students, Catherine Lee, is working on that. So we're hoping to have some answers at least. So that's a second illustration of how this Toda space and allows you to represent boundary conditions and compute things that are going with the gauge theory of a two-dimensional theory that was standing for the boundary condition. All right, and now we're moving on to the chiral rings. I should say main theorem of chiral rings. That's again a slight misstatement. Because I say nothing about the hyperkähler structure here. So I'll put it in one big page from the start, and then let's step through that. So G is going to be a compact connected Lie group. If G is disconnected, you have to add the story of twisted sectors, which I haven't looked at in detail. I think there is some work on that. E is going to be a quaternionic representation, and polarized means it's a double of a complex representation V. So some statements are easier when it's a double. And this incorporates work on Nakajima with some suggestion of what should be fairly precise suggestion what should be happening. The construction of polymorphic Gaioto, in the abelian case, they had really done everything. Later, some of these things sprinkled there, I might have to ascribe to myself. And the one key construction is due to Braverman, Finkelberg, and Nakajimas, and they really cracked, I think, the question in the polarized case, the case where E is a double. So the first statement is that, well, maybe just to go back briefly, Bezrukavnikov, Finkelberg, and Merkovich said that the Coulomb branch, functions of the Coulomb branch, so this is incorrect, there are functions on the Coulomb branch, functions on, and functions on the chiral ring, where the equivariant homologies or K-theories of the based loop group of G with Mondragon product. That was the original constructions. Now we have to see how to change that to get the other chiral rings. And this theorem is that there exist coefficient systems for homology and K-theory over the algebraic version of the loop group. So this is homotopy equivalent to the say smooth or continuous loop group divided by constant G and constant G, which is also omega G. If you do one division, equivariantly divide by the other G. So the base is the same as before. In the case of a zero representation, we're looking at the constant coefficient system, but the theorem is there are distinguished constructible and equivariant coefficient system. They're constructible with respect to the natural stratification of this space. I put a footnote 4, it's going to be point 4 below. These coefficient systems are E2 multiplicative for the Pontryagin products on their basis. And moreover, if you take equivariant cohomologies, which would be functions on these again, I don't know why I don't see, then they are even E3 multiplicative. In other words, they have a distinguished Poisson, they are commutative, but have a distinguished Poisson structure of degree -2. I prefer Poisson structure. These coefficient systems are also multiplicative in E. So remember, when E was 0, we're getting an abelian group over the base. Everything else carries an action of the Toda group scheme. It's an action with dense orbits. And in fact, there are fiber product maps from coefficients in E and coefficients in F to coefficients in the sum. I don't actually know if this is an isomorphism here. It may well be, but I realize now I forgot to check. All right. The important addition when E is not a double of a complex representation is that there are some two torsion obstructions coming in for statement 1 to hold. So that was first flagged, I believe, by Ed Witten, I think some time ago. And finally, the coefficient system are generically trivial in the sense that if you localize sufficiently much on the base, you don't notice that they are there, which means that these answers are birational to the original Coulomb branches or chiral rings for the zero representation. And they're expected to be the chiral rings again. Excessive optimism here. For E together with a Poisson structure. Another nice result is that in some cases, there's a very clean abelianization result. Namely, if E happens to contain the roots of the adjoint representation, then you can compute the chiral ring by computing it for the torus and taking away the adjoint representation from E before dividing by the Weil group. And that's an exact isomorphism. It's not a localization formula which would break on some codimension 1 regions. It's an exact statement. I'm actually, even though I note a very good topological proof of that, I mean, it is a bit intriguing. It looks a bit like it wants to be a Weil character formula, right? That's you're dividing by the Weil denominator somehow by taking out the adjoint representation. But anyway, finally, in the polarized case, I'll probably mention that quickly, there's a direct construction of the answer. So ignoring the coefficient system and the story up to actually up to every point, up to 5. There's a construction of the answer directly from the toda space and the GLSM superpotential. That's I think the main list of results on chiral rings. I mean, as far as I know, it's as far as construction, connection, topology, it's close to the state of the art. As far as geometry goes, I mean, there's a lot of work happening in connection with monopoles with singularities, and that connects to differential geometry that I'm not an expert about. There was a workshop at MSRI last fall where several people seem to have been working on new results in that direction, which were above my my understanding, I'm afraid. All right, so let's review the construction in the polarized case. Well, maybe I should stop. Are there any questions before because I've just stated a long list of results here. So before I go to the construction and to the tweaks in the non-polarized case, which is the interesting part for a topologist, maybe I should take questions.
I don't think there are any questions.
All right. So let's move on. So let's recall the construction. So I'll explain the construction morally first, because all the topology somehow is there. And the algebraic geometry comes in to make it work. What is this? So again, there are many citations to be put in from physics. I put very few of them early on. But here's a moral construction for the case when E is a double of a representation of V, so V plus V dual. So choose a polar half of E, and from that you can build the index bundle along P1 over the modulo of G bundles on P1. So the index bundle for each G bundle little p, say, over P1, you form the associated bundle, you twist by the square root of the canonical, you need Dirac operators in reality, and take the direct image sheaf along P1, you get the fibers of a virtual bundle over the modulo of G bundles on P1. Topologically, it's homotopy equivalent to the base loop group mod G or the free loop group mod G on both sides. All right, but this construction, if you use algebraic geometry, gives you a rigid object, not just a K-theory class. And this will be represented by a sheaf, actually. The sheaf actually has generally rank 0 if G is semi-simple. That's what this adjustment does. And from a sheaf, you can form an associated linear space so that the sheaf is somehow functions along the fiber-wise function along that space. It's spec sim of the dual complex. And the moral definitions that the coefficient system we're looking for are the cohomologies to compact vertical supports along the fibers of the linear space. And then you'd like to say that the chiral rings are, well, the spaces associated with the chiral rings are the specs of the equivariant homology or K-homology with coefficients in this jumping coefficient system. So each space in the fiber will have a non-trivial action of some subgroup of G, and in effect it shifts, if you like, the cohomology of the base by an Euler class. That's the effect of that, but it's happening stratum by stratum, but it's happening in a coherent topological way. Now, it's not difficult to define these homologies. Here, what's not possible in this picture to do is define the product, because what you'd like to say is that the unit for this product is the volume form on omega g. So you want to define it by integration. And that's a little difficult to make precise. In fact, I think Nakajima proposed those to try to make that precise. Now, if you want to take a TQFT point of view, what ought to happen is the product should be given by a three-dimensional pair of pans. That was on a large 3-ball minus 2 small 3-balls, and that's why it should be E3. And on that space, to solve a three-dimensional gauge-Dirac equation, with coefficients in V, and prescribe boundary conditions. I mean, by restricting to the boundary, to the outer boundary sphere, and the inner boundary sphere is supposed to get a correspondence from the moduli of solutions, and the pull back, push down along that moduli space is supposed to give a multiplication. That's what's supposed to happen. But it seems, experts tell me, it seems difficult to actually solve this equation and write the moduli space in this picture, which doesn't have a lot of symmetry to it. So the solution was found by, presented in a paper by Braverman, Finkelberg, and Nakajima. Was to replace this Dirac equation, a three-dimensional space, with an easier equation by exploiting a splitting of R3 as C times R. And the Dirac equation reduces to a d-bar equation on C, and in this case to nothing on R, because we're dealing with a TQFT, so we want to be constant in time. And once you have a d-bar equation in C, you can try something holomorphic, and indeed you will succeed. And the idea, which comes from Hecke correspondences, is replace P1 with a tiny sphere, which is a non-Hausdorff thing. It's a disk with a doubled origin, but in some way has a topology of a sphere. And you replace the correspondence, let's keep it here, the correspondence diagram coming from a solid pair of pans with the correspondence diagram familiar from Hecke correspondences. You look at bundles on the disk with triple origin. Here are your two spheres, two small spheres, and here's your one large sphere. And you have a restriction to a product of copies of bundles on the G bundles in the small sphere. This is the top sheet and the bottom sheet, and also restriction to the, if you like, outer sheet. That's a slightly bigger sphere in a pair of pans on this side. And that gives a correspondence diagram. And in this correspondence diagram, you can actually define the wrong way map. The wrong way map and then the right way map. And you get an E3 multiplication on these spaces. The way these tiny spheres move on the plane imitates E3. So you do get the correct multiplication. All right. So that's what gets around the difficulty that we can solve that equation in 3 dimensions to define the multiplication. So now I'll point out that if you just want the answer as opposed to define the construction of the coefficient system, there is, I think, an intriguing global answer which reconstructs the chiral ring just from the original Toda space and the GRSM superpotential. Namely, you take that section given by the GRSM superpotential, exponential of dW of a Toda space, and use it to shift the Toda space vertically. And take two copies of the space and glue them together along this vertical shift, this vertical shear. Now, if this section was regular, of course, you would get taking two copies and identifying them by an isomorphism would give you exactly one copy of the original space. So you'd get exactly the original Toda space back. But this section has singularities. And the singularity is going to force some crushing of the result. So another way to say it is that the chiral ring for the representation E is going to be a subring of functions in the original total space, and they're the functions which can survive, meaning remain regular under this translation. So that will force some vanishing conditions, which you can spell out very explicitly. It's something that reminiscent a bit of toric geometry, what happens when you start blowing up based on some combinatorial data. And my former student and collaborator Dan Pomerleano found a nice formulation, abstract formulation in terms of quantum cohomology. The ring of functions in the total space, as I will explain again in the next lecture, acts on the symplectic cohomology of open manifolds of G action. In this case, the symplectic cohomology contains a lattice inside. This is essentially like a Laurent polynomial ring, and this is like a Taylor, like a genuine polynomial ring. So it contains a lattice of quantum cohomology, and the Coulomb branch is exactly a subring which preserves the quantum cohomology lattice inside symplectic cohomology, provided you also include the bulk deformations of quantum cohomology. So there is an intrinsic description without even saying what the GLSM superpotential is. Interestingly enough, we don't know if this is a general theorem, but one could always try. All right, last thing I'd like to discuss is what happens in the non-polarized case. And I should say here, I don't yet have a good interpretation in terms of Gromov-Witten boundary condition or a superpotential the way I did in the polarized case, where I could choose a V. And it looks like there should be an interpretation in terms of a V bundle over the flag variety G mod T. So notice that even if E is not split, not polarized over the group G, once you restrict to maximal torus, of course it splits, which means that over G of the flag variety, you can find a family of Lagrangians that way. And I can give a formula for the Coulomb branch, which has some similarities with this, and that involves the maximal torus and the Weil group, but is not clean enough for me to see it, if I could say it in terms of some quantum cohomologies or symplectic cohomologies of these manifolds. I think that's a good question, but which I can't answer now. And by the way, I should give you a caution. If you want to look at the paper, you should check the version on my website. The one on the archive has lots of calculational mistakes. I will replace it when I'm pretty sure I fixed all of them. But there are so many calculations there that could still have mistakes. The one on my website has no known mistakes. Let's put it that way. So that's the reference version for now. All right, so let's go back to the problem. Let's say we try to imitate the Braverman-Finkelberg-Nakajima construction and say, oh, forget about V because V doesn't exist. Let's use it for E, for the whole representation. But of course, what you construct is a chiral ring for the double representation, E plus E dual, or actually two copies of E. You build that. So the coefficient system you build, which were built from Euler classes or some vector spaces, are not twice as big, but are the squares of what they should be for E. So you need to extract square roots of these coefficient systems. The coefficient systems you build are multiplicative in E, not additive. Okay, what's a good way to extract square roots of something built from a complex vector space? Well, you need something of half the dimension, the Euler class of something half the dimension. And one way to get something of half the dimension is to find a real structure on your space. Right. So I have to investigate whether these index bundles which we use to construct that sheaf have real structures on them. Right. So we start with a representation that's a map from BG to the classifying space of a symplectic group. And by the time we take the index, it means we're looping this twice. And we get a map, of course, from a loop space of G, a G equivariant map to the double looping of PSP. And going back to what Bott taught us many years ago, that's also double suspension of KO. Now, double suspension of KO has an interesting Chiaro is the base of an interesting vibration. This sometimes is called Wood sequence. And people reference apparently an unpublished manuscript by Wood, but it is implicit, of course, in Bott's work on periodicity for real K-theory. So this vibration, the total space is Ku, the classifying space for complex K-theory, and the fiber is the classifying space for real K-theory, and the base is sigma 2 Ko. And this vibration is classified by a map to, of course, the looping of Ko, and that's actually the map eta from sigma 2 Ko to Ko. Eta is a class in Ko minus 1 of a point. So just cap with that and reduce, shift down, so to speak. All right, the polarization of E.
Just a
yes.
quick question. Could you just say again why the double loop space is relevant here?
Well, because double loop space is the index over P1. That is. So where are we?
Yep.
Here, I think. So Bungie of P1. These are really maps from the two sphere to BG, topological. That's how it arises. So that's where we're trying to construct a bundle. So now I'm investigating what reality structure we have on a bundle, assuming we're exploiting the fact that the representation wasn't just complex, but quaternionic. Right, so before we're using V, which was a half of E, and we're exploiting nothing. Now we don't have V, we just know E is quaternionic, and I'm asking, okay, what can we learn from that? All right. So we have this vibration, and well, to be able to lift this map here, we would need to kill the composition with eta here. If you had the polarization of E, you already get a lift to K. That's what exactly what we give. We give a half. This map here is a quaternionic doubling. So center representation V to V plus V star. Quaternionic. Sigma omega 2 of that. So it's actually skew quaternionic. It's V minus V star, I lied. It's V minus V star at this point. One is even, one is odd. And you have to specify the duality operator where it squares to 1 or minus 1. I forgot for sigma 2, you get one rule. For sigma 6, you get another rule. No, I forgot which one it is. But anyway, this is the map which goes to sigma 2 of Ko. So that pins it down. All right. So the obstruction to having a lifting in general would be, of course, the composition all the way to sigma Ko. It's the eta invariant applied to omega 2, the looping of the the double looping of the representation. But even that would not be enough, because in the end, we want what we get to be multiplicative. Multiplicative, in fact, E2 multiplicative. So actually, the obstruction to what we want to do has to be measured back here, has to be de-looped twice, and the obstruction is eta applied to the original representation E. But lifting eta is the same as polarizing E. In other words, saying that E is not polarizable is saying exactly that this composition is not zero, so you can't do it. You cannot construct this lifting here so that it's E2 multiplicative. So it seems that we've done nothing with all this analysis until we recall that we don't actually need, it's very ambitious to construct here a lift of the map. We don't need that. We need to lift enough to build our coefficient systems. Okay, so I think this is written a bit too topologically. What we need to do is figure out what happens to this linear system when we map it as a governing coefficient system for homology or for K-theory. And what the map is that does it is, in this case, it's, I think if I got my numbers right, the shift of the so-called J homomorphism that starts from the orthogonal group and maps to the sphere. And it lands to sigma 4 of GL1 of homology or sigma 4 of GL1 of K-theory. So it tells you how those coefficient systems act on homology or K-theory, or KO theory, if you care about that. And what happens that under this map, most of the information from the vector bundle is lost because of a Thom isomorphism. Almost nothing survives. Remember, the Thom isomorphism in homology is obstructed only by orientability, requires only orientability, so it's obstructed by W1. And K theory requires orientability and spin C structures, W1 and W3. Or in KO theory, W1, W2. So the only obstruction, we don't care about the obstruction to lifting here, we only care about the image after you apply W1, W2, which are shifted up a bit. So when you trace the obstruction, you have to find out is that for cohomology, the obstruction class, it lives in H4 of BG with Z mod 2 from here, and it's W4 of E or C2 mod 2. That's the first obstruction class you get, which obstructs orientability of the coefficient system. For KO theory, a secondary obstruction is W2. The secondary obstruction is only defined if you can lift the first obstruction. That's something interesting. What happens when you start delooping these spaces, you can no longer separate W2 from W1. But if you kill W1, then you can define W2 and you can ask if it's 0. And for KU theory, there's a class in H6 of BG with Z coefficients, but it's always a two-torsion class. And in effect, it's a half of the third-Chern class. Now, E is quaternionic, so the third-Chern class vanishes. That tells you that any half of the third-Chern class is two-torsion. It's tricky to get your hands on it, actually. And little exercise in topology, if somebody has given you a half of the second-Chern class of something, then you'll be able to produce a half of the third-Chern class, a distinguished half. And that's one we're after. All right. Now a theorem which follows from a very nasty calculation. I'm embarrassed that I haven't been able to find an intelligent explanation. Is that for connected groups, only for connected groups, if the first obstruction vanishes and the second obstruction, meaning if the obstruction to building the homological chiral ring vanishes, then so does the obstruction to building the K30 chiral ring. I see technically my time is up if I'm counting correctly, and I'm almost done. So let me just display the last thing because it is important to connect to the literature. It's easy to weaken the obstruction with a bit of the trick so that you don't need W4 to vanish, you just need to be the square of an integral class. And that's what explains why polarized representation always work. They don't always have vanishing W4, but W4 is always a square of a first-Chern class. So they always work. And finally, something intriguing is that one can even improve the obstruction to reduce to something that's predicted by Ed Witten, provided you abandon the Z grading on homology. You just need the square root in Z mod 2, in H2 Z2 coefficient. Doesn't have to be a Chern class of first Chern class of something. But if you're willing to accept that, then you'll be forced to collapse the grading in homology mod 2 as well. So I think, as I said, I'm clearly over time, so maybe it's a good time to stop.
Any questions?
Yeah, thanks. Can I ask which prediction by Witten is being referred to here?
So I think the form in which Witten described the obstruction, I think he claimed, I think for connected groups, I'm sure I didn't see the original paper, but yeah, let's put it here. So Witten obstruction is image of pi 4 of G in pi 4 of SP under E.
Yeah, okay.
It's not obvious, but it's equivalent. It's equivalent to this one, to having a square root mod 2. I think for connected groups. For disconnected groups, that doesn't work at all. For disconnected groups, that's not true. The secondary obstruction can appear independently of that.
So the way that first appeared, that was an obstruction to something completely different. right? It was an abstraction to, it was a gauge anomaly in 4-dimensional gauge theories. So it's an abstraction to summing over gauge bundles in 4D accurately, which is why Pi4 is showing up. And the same thing is appearing here, and I sort of wonder why.
That has
there
been
should be-
claimed. That has been claimed. I do not know the original source. I have heard that claim. What I can assure you is that the only thing I can assure is that this being non-zero is equivalent to actually it's equivalent to probably to even the first one failing, meaning no, it's equivalent to W4 does not have a square root in H2 with Z2 coefficient. It's equivalent to that. That takes some case by case checking. It's actually not very difficult to show that if G does not contain symplectic factors and is connected, there will be no obstruction. The symplectic factors in G are the only source of trouble. That's not too difficult.
So a related question, just to clarify what you just said. So the problem you set out was to start with the theory of with double the matter, and figure out how to take a square root in this algebraic construction. Do you have any sense of whether that's just some fundamental obstruction to defining Coulomb branches at all, or for a theory with non
you mean when there is
when
there is an obstruction, or what do you?
I mean, there might be another way to do it, right? That doesn't involve the BFN construction. Like you initially mentioned, like solutions to Dirac equations.
No, I think there is a. I mean, so I know another place where it shows up in terms of the representation theory. You can do some kind of a Koszul dual of that. You can build something, a bundle of tensor categories, and to be able to return to the space, the underlying space, you need to construct a fiber functor for that. And that is obstructed. You kind of have a double cover of a fiber functor instead of a fiber functor. So I know another place, I know a restatement of the problem where the obstruction shows up in a very hard way, but of course, this is modulo accepting that these really are the chiral rings.
Right.
So
thanks.
It's
So this double cover of the fiber functor, is this that it like lands in super vector spaces?
no, I think I believe it's obstructed whether you want it in, I mean, a priori you want to land in super vector space, because a priori, even though we're seeing even degrees coming up, for example, if they needn't have been. So a priori, I suppose you want to allow super vector space from the start. Even then, you have a problem with the fiber functor, if I recall the calculation. There's another interpretation of the obstruction is that it's like a curving. The coefficient system is not flat; it's curved. That's another way to interpret the obstruction. That's more or less the curvature, or some characteristic 2 version of the curvature. So there are many interpretations which suggest that really it's an obstruction to something. But I'm not saying it's an obstruction. Is it obvious an obstruction to a topological theory existing? That's a little less obvious, because you might be able to, well, depending how much you want or little you want to categorify it. So.
Hello. I'd wonder whether, I mean, you might get a spin TQFT or like with some sufficient reduction of, or with some sufficient extra structure, tweaking the product. And I can, so the space of local operators on just at a point should be defined anyway, but the product may look strange.
Yes, the obstruction is to defining the multiplication. That's correct. That's where you hit it.
So
for example,
I'm not sure, but I can imagine that throwing it, like working with spin manifolds and keeping track of spin structures, that might.
That doesn't seem
or
to fix it,
something
because
like
for E3 structures, you see a unique spin structure on the sphere, two sphere, unlike the circle. So it doesn't.
It's trivial. Yeah.
That doesn't obviously help,
Yeah,
because
thanks.
I couldn't see a way to an easy way at least to solve it by that method. But I mean, I think it is a good question of exactly what it means that the construction is obstructive. I mean, but every version of the construction I know is obstructive. When you try the algebraic recipe you can derive, you finally need to take some square roots of functions which aren't there. So
Thanks.
Any other questions? All right, let's thank Constantine again.